This is problem number 3 related to design of beam subjected to torsion. This question was asked in April 2017 for 16 marks. Let first I read this question. Design the beam for the following data. Bending moment 42 kN, shear force 30 kN, twisting moment 12 kN. Assume the width of the beam 300 mm. Design the beam for the torsion effect. Use M20 and Fe415. So what is the difference of given data in this question and previous two questions? That is, the depth of beam is not given in this question. You have to find out the depth of beam and then you have to solve the question. Okay. So first I want to alert you that is the given, all these things are given data, bending moment, shear force and twisting moment is not in ultimate condition. You have to convert this value in ultimate condition by multiplying 1.5. So bending moment, then what is the ultimate bending moment? I will write here. Ultimate bending moment mu, it is 42 into 1.5, 42 into 1.5 is 63 kilonewton meter. Then torsional moment TU, torsional moment 12 into 1.5 is 18 kilonewton meter. Shear force VU is 30 into 1.5, it is 45 kilonewton. So this is the main given data in this question. Okay, I will run this. Width of the section is given. Width of the section is 300 mm. Okay, depth is absent. You have to use the M20 and Fe415 material combination to solve the problem. Okay. Now, first thing, I want to solve the question like whatever we solved the previous two problems. That steps I don't want to change. Okay. Step number 1 is the equivalent shear force. It is VE. Equivalent shear force is VE. So VE is equal to VU plus 1.6 TU upon V. Okay. You know the value. VU is 45. 1.6. TU is 18 divided by 0.3. Okay. TU is 18 divided by 0.3. So 18 divided by 0.3 into 1.6. 96. So 45 plus 96. So this value is 141. 141 kilonewton. Okay. So again I want to check this. 18 divided by 0.3 into 1.6 plus 45. VU is 45. Okay. So it is 141, correct. Step number 2. Equivalent shear stress. Equivalent shear stress tau VE. Okay. So tau VE is equal to VE divided by V into T. Now we require the depth of the section. So for that, to avoid the iterative method, assume directly capital D by V ratio is 1.5. Capital D by V ratio is 1.5. So capital D by, we know the width is 300 into 1.5. Okay, 1.5. So depth is 1.5 into 300. It is 450. It is 450. Okay. So the overall depth is 450. Then assume effective cover 35 mm. So effective depth is 450 minus 35 is 415. 415 mm. This is the effective depth. Like this, to avoid the iterative method to find out the depth. So this is the easiest one. So it is 141 into 10 raised to 3 divided by 300 into 415. Okay. So 141, 300 into 415. The value is 1.13 megapascal. 1.13 megapascal. So this is the tau V. Now, next is again assume PT 0.5%. If you assume the PT 0.5% from the table 19, page number 73 of IS 456-2000 version, the value of tau C is 0.48 megapascal for M20 grade concrete. This is for M20 grade concrete. And the value of tau C max is 2.8 megapascal for M20 grade concrete. But this value is taken from table 20. Okay. Well, comparing, tau C max is more than tau VT is more than tau C. That is 2.8 is more than 1.13 is more than 0.48. Shear and longitudinal. Shear and longitudinal reinforcement required. So you have to design the shear and longitudinal reinforcement both. Is it clear? So this is your step number 2. So write down the value of tau VE. Tau V is 1.13 megapascal. Okay. Now what is the next step? What is the next step? Design the longitudinal reinforcement. Design longitudinal reinforcement. Design longitudinal reinforcement required first ME1. Okay. So ME1 is equal to MU plus MT. So MT is TU into 1 plus capital D by B divided by 1.7. So this is the ME1. What is the MU? MU is 63, TU is 18. Okay, 1 plus, we know the D by B ratio is 2, 1.7. Okay, so 3 divided by 1.7 into 18. So this is 31.76. This is 63. If you add this, we get the value 94.76 kilonewton meter. So this is the ME1. This is the ME1. So let's check that the provided depth is sufficient to take the ME1 moment or not. For that, what you have to do? So ME1 is equal to mu are balanced. So mu1 is equal to 0.138 FCK BD square. If we equate this, we can find out the sufficient depth for the mu1, whether our provided depth is sufficient to take this mu1 or not. That you have to check. Okay. So mu1 is 94.76 into 10 raised to 6. 0.138 HK is 20. Width is 300. Have to find out the depth. So what is the depth required? What is the depth required? So 94.76 into 10 to 6 divided by 0.13 FCK is 20. Width is 300. Depth is 4. Sorry, we have to find out the depth. We have to find out the depth. Okay. And the root of answer, required depth is 338.296 mm. That means if you want to carry the bending moment 94.76, the depth of beam required is 338.296. That means our provided depth is 415. So it is okay. So depth provided is 415 mm. So the beam is safe to take this bending moment. Again, the provided depth is more, required depth is less. That means our mu1 is less than mu are balanced. So the section is acting as under reinforced section. Okay, the beam is satisfying this criteria. That means the mu1 is less than mu are balanced. The section is acting as an under reinforced section. If the section is acting as an under reinforced section, so directly find out the steel. Okay, so we need here we need the value of MT. MT is only 31.76 kilonewton meter. MT is only 31.76 kilonewton meter. Okay, is it clear? What we have to do? Yes. So directly find out the steel. So tension steel. You have to use that AST form. AST is equal to 0.5 FCK divided by F into bracket 1 minus under root of 1.6 into ME1 divided by FCK BD square into BD. But we need the value of ME1. 0.5 FCK is 20. Fy is 415. 1 minus under root of 1 minus 4.6 ME1. What is the ME1? ME1 is 31.76 plus MU is 63. It is 94.76. 94.76 into 10 raised to 6 divided by FCK is 20. Width is 300. Depth is 415 square. 300 into 415. Okay. So that calculate the steel. So 94.76 into 4.6 divided by 20 into. Okay, I will calculate it. 0.421. 1 minus 0.421 under root of answer. It is 0.760. 1 minus 0.760 into 0.5 into 20 divided by 415 into 300 into 415. So I have to calculate again. 94.76 into 4.6 divided by 20 into 300 into 415 into 415. Okay, this is 0.421. 1 minus 0.421 under root of answer. Okay, it is 0.760. 1 minus 0.760 into 0.5 into 20 divided by 415. Okay, into 300 into 415. Value is 720 mm square. Value is 720 mm square. Okay, so this is the value. Please check this value. So assume 16 mm bar and provide the number of bars. It is 3.58. That means you have to provide the 4 numbers. Okay, but what about the compression steel? What about the compression steel? If numerical value mt exceeds the numerical value mu, mt is 31.76, mu is 63. So this value not exceeding the mu, so compression steel is not required. Compression steel is not required. Okay, but provide the minimum anchor bars same as the tension steel. Now final shear reinforcement. Step number 4. Shear reinforcement. Okay, so for that first we have to sketch the diagram. So I want to sketch this diagram here. Okay, so this is the beam. This is the alignment of tension and compression steel. Okay, alignment axis. Provide a 16 mm bar diameter 2 at top. Provide a 16 mm bar diameter 4 at bottom, because it is. Now what is the width of the section? It is 300. The depth of the section is 450. The section is 450. Okay, so if we consider 35 mm from this side, 35 mm from this side, so the value of B1 is 300 minus 70. 300 minus 35 from this side, 35 from this side, 300 minus 70 is 230. It is 230. And what is the D1? D1 is 450 minus 70. It is 380. It is 380. I will write here. D1 is equal to 380 mm. Total 450 minus 35 from this side, 35 from top. Now if you assume the 8 mm diameter 2-legged stirrups, if you assume the 8 mm diameter 2-legged stirrups, okay, so this is the x1, okay, and this is the y1. Okay, so for that you have to assume 8 mm diameter 2-legged stirrups. Okay, so first we have to find out the x1 and y1. What is the x1? X1 is this distance to this distance is 230 plus half diameter of this bar. Half diameter of this bar is nothing but a 16, and half diameter of the legs, it is 8. That means it is 230 plus 16 plus 230 plus 16 plus 8, it is 254. Okay. Now what is the y1? Y1 is 380 plus half of this diameter is 16 because this is 8, 16 mm diameter, half of the 16 is 8, half of the 16 is 8. So add 8 plus 8 is 16 and plus 8 is 380 plus 16 plus 8, it is a 404. These are the values. Okay, x1 is 254 mm and y1 is 404 mm. Okay, so these are the calculations of x1 and y1. Now directly find out the spacing. Spacing first is ASV is equal to PU into SV divided by B1 D1 into 0.87 FY, BU into SV divided by 2.5 D1 into 0.87 FY. If you put this value in bracket, okay, so what is the ASV? ASV is the area of one stirrup bar multiplied by legs. ASV is equal to area of one stirrup bar multiplied by legs. Area of one stirrup bar is 5/4 8 square. Two-legged. We know the answer is 100.53 mm square from our previous problem. Okay, so it is 100.53. TU is 18 into 10 raised to 6. SV spacing is find out. B1 is 230. D1 is 380 into 0.87 FY is 415 plus VU is 45 into 10 raised to 3. SV we have to find out. 2.5 D1 is 380 into 0.87 FY. Okay, so directly I am going to find out the spacing using this formula. Okay, so it is 18 into 10 divided by B1 into D1 into 0.87 FY. Okay, this is point. This particular value is 0.570 SV. Okay, 45 into 10 raised to divided by 2.5 into 380 into 0.87 FY. Okay, so this value is, this particular value is 0.1311 SV. Okay, now 100.53 divided by 0.570 plus 0.1311. The spacing is 143.38 mm using this first formula. Second formula is ASV is equal to tau B minus tau C divided by 187 Fy and to multiply by B into SV. So it is 100.53. We know the value tau V is 1.13, tau C is 0.48, width is 300. You have to find out the spacing divided by 187 Fy is 415. Let's find out the spacing. 1.13 minus 0.48 into 300 into 1.13 minus 0.48 into 300 divided by 0.87 Fy 415. It is I have to calculate again. 1.13 minus 0.48, okay, into width is 300 divided by 0.87 Fy. This value is 0.54. This value is 0.54 SV. This value is 0.54 SV. So 100.53 divided by 0.54. Okay. The value is 185.98 mm. The spacing from second formula is 185.94 mm. The spacing should not be more than, the spacing calculated from these two formulas should not be more than x1 is 254 mm, then x1 plus y1 by 4, x1 is 254 plus 404 divided by 4. So 254 plus 404 divided by 4, the value is 164.5 mm, and third is 300 mm. Okay. So these two calculated values should not be more than these three values. So you have to select the minimum value from this 5 value. 1, 2, 3, 4, 5. The minimum value is it is 140. It is 140. So say I 140 center to center. 140 center to center. Is it clear? How to find out the spacing? Is it clear? How to find out the spacing? So the final reinforcement details are, okay. So we have the 300 mm width, 450 overall depth. Okay, so these are the two bars of 16 mm diameter. These are the 4 bars of 16 mm diameter for the tension steel. This is the 8 mm two-legged 140 center to center stirrups. Okay, so this is the total reinforcement details. The overall depth of beam, okay, if it exceeds 450 mm, but overall depth of beam is not exceeding 450 mm, side face reinforcement is not required. Okay, side face steel is not required. Side face steel is not required. Side face steel is not required. Okay.